Hello, everyone. Welcome to ITS 350. Today's Thursday. We're gonna continue our discussion that we started on Tuesday. Just a few reminders. So this next Monday and Tuesday is fall break, so there will be no class on Tuesday. And then we will meet again on Thursday to go over labs. So this week I'm not going to assign homework. Okay, so that way, you know, you can have maybe rest up during the fall break. And then I'm also almost done with the grading for you guys. So hopefully you'll have that sometime, you know, by the weekend. You'll have everything graded. Okay. So yeah, so that's the plan. Given that we don't have class on Tuesday, I'm going to go over a brief lecture today, just, you know, a little bit. And then after that, I'm just going to open it up as an open lab. If you have any questions about anything or anything like that, we can go over topics in the lab. So that's the plan. Are there any questions before I begin?
I have one question just to clarify. So the lab that's available now is not due next Thursday, it's due the following Thursday, right?
So let's see your question. Let me go to Brightspace and then let's go to content. And so today you have a lab due, correct? Which is RSA?
Yeah, the PKI-B.
PKI-B, right. That's due tonight. So if you have questions about that one today, you know, I'll give some time at the end to you know, just open it up, open lab. Otherwise, the next thing we would have is these two. PyCrypto, we haven't gotten there, so we're not even close to that one yet, this module. I guess I've added some materials, but that's not something we have started. XOR is the one topic that I will cover next Thursday. Okay, so because it relates to implementing the data encryption standard, for instance, and so I think we need a little bit more background on the algorithm before we can actually try to implement it. So with this one, this is a pure coding Python lab. There's really just one problem, I think. So I'm really gonna walk you through this one. Okay, I'm gonna sit with you guys, and then I may leave some things as I do sometimes open for you to solve, but we're writing it from scratch, so I have to give you a lot of background on that. So therefore, there's no homework assignment currently.
Okay, gotcha.
All right.
Thank you. I appreciate it.
Yeah. Okay. All right. So that being said, as I said, so we are gravitating towards this, but I'll just begin it Thursday. You know, there's no class on Tuesday, so I might as well make today a little bit of a lecture and in advance a little bit more on that topic. And then after that, as I said, just open lab, any questions? All right, so are there any other questions before I begin?
Not that I can think of, at least.
All right, good. All right, so then, again, one thing, don't forget to submit your RSA or PKI-B lab. Make sure, and if you have questions, I know that one had a little bit more coding, so if you had questions on that, you know, you should ask them today. All right, so you'll have to remind me kind of where we were. I believe we started stream ciphers last week or Tuesday. We talked about pseudorandom generators. We talked about the pseudorandom key and how it mimics the one-time pad. Okay, so I believe we covered all of that. All right, so then yeah, so the stream cipher So I know you guys had some questions about stream ciphers, but do you need me to address something further on those, or would you consider that you understand them at this time?
I'd say understand it because you kind of re-explained it last class and went a little bit more in depth in it. So after that, kind of got it.
Okay, all right. So then, yeah, so that's really all there is to that. As you can see, I mean, we would break the message into blocks. Only the blocks would be, you know, size 1 byte, and then we would need to have a pseudo-random function, which, you know, Python is great for that. And that's it. I mean, the function would give us a byte, so it's kind of in a for loop. We would grab the block, we would grab the pseudo-random key byte, XOR them, and kind of obtain, you know, our cipher, and then send that cipher along. So that's really the plan. Very similar to block ciphers, if you think about it, except with the block ciphers, we would have, you know, it's a little bit more complex as we start to look at the algorithms. And with the stream cipher, basically the additional thing is to have that pseudo-random function. But the pseudo-random function is not something we're going to create from scratch. You know, we're just going to use something that's already built in. All right, so if that's the case, that we've covered stream ciphers, then we should be ready now to cover block ciphers. All right, so get back into block ciphers into a little bit more detail. I'm also checking my RSA notes, and I believe that I have completed that topic as well. So we've gone over the code, we've gone over the algorithms, the scripts, and I guess you guys will ask questions if you have them. So yeah, so I do believe this one is also done. So then that leaves, you know, block ciphers, which should be pretty interesting, because now, if you remember before when we looked at block ciphers, we kind of just did like a very high level view of block ciphers. Whereas now, we get to go into the details. So just like we went into, if you remember, I introduced symmetric key encryptions. We kind of looked at it from a high level point of view. Then I introduced asymmetric encryption, and we looked at it from a high level point of view, and then we went into depth of the RSA algorithm and everything like that. So now we're kind of doing the same, but for block ciphers. So we're going back to block ciphers, and we're going to go into more depth to define it a little bit more formally. We're going to have a more formal definition of it. And this one, just like we did with RSA, we're going to end up with the actual code for it, you know, an implementation of this one. By the nature of a simple algorithm like this, we can actually implement a lot of it from scratch. However, we're not going to go into all the details of it. We will just implement, you know, a simple, one of the modes of operation, for instance. You'll see the difference between ECB and CBC, something like that. We may not get into the details of the algorithm of DES, because it does get a little bit more complex. But I will give you, you know, so we won't do the Python of it, but we will look at the pseudocode, basically, I guess, the algorithm itself. So block cipher. So let's go back to that idea. All right. So that really takes us back to the very first week when we talked about modes of operation, right? Chaining modes, ECB, CBC. And, you know, it takes us back to XOR, and it takes us back to breaking the block or the message into blocks, right? And encrypting them. That's what we're going to be doing now. So the key idea with block ciphers, the key idea with a block cipher is the mapping. So key idea is that it maps n bits. So it maps, oops. it maps n bits of input to n bits of output. So it's pretty simple, really. You know, and you understand it, right? You have a message, it's got blocks over here, and then you do some kind of a XORing with a key, and then that gives us the cipher, right? So whereas this is the plain, we get the cipher, but they are actually of the same dimensions. So this is the same dimensions, right? So that's why what's important here is that we are mapping from n bits to n bits, okay? N bits of input to n bits of output, right? That's the key idea in block ciphers. So here we have, for instance, then we have the plain text message, plain text block, okay? And this is n bits, and then we're gonna run this through, you know, some kind of a algorithm, right? That's gonna be encryption and decryption, right? Given some key. Remember here, this is not public and private key anymore. We're back to just one key, which is the secret key. Now the key can be, doesn't have to be of n bits, as we know. It is actually k bits, and it's smaller, right? K bits. These are the algorithms, basically. These are the algorithms. Okay, and that's what we're going to focus on today. So you really should have an understanding of everything else that I have here written in red, basically. But we never really went into the details of the algorithms. So here we have the ciphertext block. Okay, so that's really, and the key thing is this is n bits, and this is also n bits, okay? So now the classic example of the algorithms, right? So I'm gonna mark it in blue now. So I'm talking about the algorithms. So the classic examples of algorithms are gonna be, you know, DES, triple DES, AES, and so on. So we will not cover AES because AES does become a little bit more complex, and you'll see that, you know, but at least we're going to cover DES to the point. So at least we're going to cover DES to the point that, you know, it should make a little bit more. It should make sense how the other ones kind of work. All right, so that's really the idea. So remember, with these algorithms, what's important is, you know, the block size. The block size, for instance, for these is gonna be, you know, n, basically the n. Switch over to another color. N is gonna be 64 bits, for instance, right? And then with AES, have more computing power because it came later in time. So then this one becomes, let's say, you know, 128. Oops, can't write today. It becomes 128 bits, so it's a little bit bigger. And you know, hopefully as you're practicing, especially your performance lab last week, you saw, you know, the bigger we make these things, the slower the algorithm. So these are important values, but at the same time, the more secure, right? The harder it would be to break. Now, if we were talking about key size, that's going to be the K value, and it's, you know, could be something bigger than the block, 168 bits. This one could be, 256 bits, right, and so on. So we will see today how, hopefully, we'll get to that today, how, okay, but why is the block not the same size as the key? So how do you handle that, right? How do you handle that? And so we're going to have to understand that. We're going to have to understand that in the algorithm itself, right? So how is that handled? But you'll see it's just pretty basic programming logic, to be honest. Okay. Let's switch back to red. Okay, so we've talked about block ciphers like that. So now, remember, now I'm getting into the algorithm itself, right? So what I'm going to give you is the algorithm. And like I said, my goal, this is not a programming class. I expect you guys to have taken programming in other courses, but but you should have the logic, right? And so I'm going to stress the algorithm, and Python is a very good language for this. It's in your book throughout. The other option was C, and I do believe Python is probably a little bit more friendly than C. All right, so let's look at this algorithm for block ciphers. It's just a generic one or general one. We're going to look at it from the point of view of just general one and steps, basically. So we're going to say, first of all, we're going to say that block ciphers, so block ciphers are typically built by iteration. I had a student, I remember, I just remember this, maybe a couple of years ago, and we did the encryption of the first lab, the secret key with the images, if you remember. And then we did this lab where I'm asking them to literally, if you remember in that lab, you used AES or DES and you just encrypted the images because it was a symmetric key lab using OpenSSL. And then you could see like the ECB, CBC, all those modes of operation. So since here we're discussing that idea of ECB versus CBC in the algorithm, I didn't make it a part of the homework, but I remember he was so curious that he just decided, I'm going to implement this algorithm, which wasn't as advanced as AES, but it still captures the modes of operation. And then he said, you know what, I'm going to take those images and I'm going to figure out how to encrypt them. And he actually ended up taking the images, converting them into data in the Python script, running it through his own code, and he was still able to get the same results where, in ECB, as you know, the image shows pattern. In CBC, it does not show the pattern. So he literally coded all of that, and just out of curiosity. And, I thought, it was pretty neat. All right, so so we were talking about block ciphers, and the key idea here is that they are iterative. Okay. So, sorry, I just got a question. Yeah, so I got a question from someone about some question on the exam, question 2. So we can talk about it, but it was something to do with the stream cipher. I didn't think that answer. Actually, stream cipher, the fact that we discussed it on Tuesday should clarify why I took off points there. So the key thing, okay, so I had a question about what's the difference between block cipher and stream cipher, right? So most of you would know that the key idea there, as I've said, is that the block cipher uses a block of a specific size, let's say 128 bytes, whereas stream cipher is what? What would you guys say is the main thing about a stream cipher? that's different from a block cipher?
It performs bitwise operations, so no
Bit-
padding is needed or anything like that.
Exactly. So it's on a per byte. Exactly. Very good answer. Right? It's on a per byte basis. So that's why it's called a stream. So you don't grab, blocks. You just kind of grab it on a per byte basis, and then you run it through a key. So yes, you can use a pseudo-random key, but that's not really the main concept, right? The main difference is this idea of breaking things up into bigger blocks versus breaking things up into smaller, per byte basis. All right, but if you guys have more questions, just send them my way. Okay, so let's continue here. So block ciphers are typically built by iteration, and what that means is, you have a message, right? This is the block cipher. With a stream cipher, you just grab a little byte, send it, and then you have keys on both, right? So there's a key, another key. This also, the key here will be a key of a certain size, whereas this key is really the size of the byte. So the plain text byte versus the plain text key byte, or the plain text byte versus the key byte, and those two get XORed and it gets sent, right? Both of these approaches, A and B, are iterative. So block ciphers are typically built by iteration, all right? So that means you kind of use a for loop. And so where I'm going with this idea of the algorithm is that we're going to have for loops, okay? So they're built by iteration. So one of the challenges that you might find with this initially is breaking up the input into blocks, okay? So that's one thing that I will provide is how to do that. Usually I just, I'll create a list of blocks and then I'll, for block in list of blocks. But getting that list of blocks is the trick, right? So I'm going to create a function for that, and that will take the message, calculate the length of the message, the size of the block. Padding, as Dakota said, we got to do padding in blocks, and all of those little details will have to be addressed, okay? So that's where I'm going with this, is that now we're getting a little bit deeper, just like we did with RSA, we're getting a little bit deeper into the mechanics. The great thing about this is that with RSA, we had to use a lot of algorithms, right? That are already there for getting us that D parameter and all of that. Whereas with this one, we're actually writing a lot of this code without the help. Although both this one and the RSA were written from scratch, no libraries, still the complexity of RSA was a little bit more than the complexity of this one. Right? So that's another thing that I want you to look at, okay? Maybe at the end of the semester, we will come back to that RSA. If time permits, we'll come back to that RSA and get into those other algorithms. But the problem is with that is that I wish you guys had a little bit more background in Python for us to really dig deep into that. But given that you don't at this stage, that's why I'm not getting so much into the details of it. All right, so we do the block ciphers, right, and are typically built on iteration. So they're typically built on iteration. So let's look at it from the point of view of steps. I'm going to do step 1, all right, and that's, you're going to get a key. You get a key. Okay, so you get a key, such as for des, it would be, let's say, 128 bits. And you want it to be as random as possible. Remember that that's the key. That's why maybe you guys have heard of like quantum computing, and how in particular people that work on quantum or physics related computing, one thing that they have built are apparatus that generate keys, because it is believed that by the nature of physics and quantum physics, things are the most random in those environments. And so what they are selling sometimes, the products that they sell are these, you know, quantum enabled or whatever you want to call them, enhanced devices that produce nothing more than a 128 bit sequence. But the advantage of that, supposedly, as they sell it, is that, you know, which is based on the physics, which is obviously quite highly supported. What they're selling is that these keys are more random than other keys. So for highly secure things, you know, that might be the way to go, or it's certainly something to explore as research. All right, so so the first thing is you establish the key. So I've mentioned that. Remember, randomness is extremely important. So as random as possible. Okay. All right. Then step two, you're going to what is called expand the key into a sequence of keys, which are called the round keys. Okay. So as I said, so now we're getting into more of the details of these algorithms. So in fact, it turns out that you don't always just have one key. In the algorithm, you have functions that will, just like the pseudo-random function generated a very long key from a small key, it's kind of the same idea. Here in block ciphers, you generate what is called the set of round keys from the original key, but it's a function also in the algorithm, and so it's going to be deterministic, so you can use it inside, right? And that provides some efficiencies. So the round keys is basically, it's an expand, so you basically expand the original key, expand the key into a sequence, of keys, and that's called the round keys. Okay. Then step three, look at step three. You're going to now encrypt the message. So the message is encrypted using these keys. So encrypt message using round keys. Okay, so that, here we have R given K given the message, right? And that's sort of the algorithm of the round keys. You just give it the original key. You give it the plain text message in this case. And so this, we're going to call this function over here, as you might imagine, the round function. Okay, so this is the round function. Okay. So the inputs, as you can see already, it's going to be the current key, or the secret key, the shared key, and then the current state of the message, right? So wherever you are in the iteration, that's the block that you're trying to encrypt. Okay. All right. Then in step four, or another step, let's say step four, you need to break the message into blocks. So break message into corresponding blocks. Okay. So for instance, you have a message over here and it's got some data, right? And it's going to be broken up into blocks of 128, 128. But notice this one comes up a little short, so we're going to have to pad it so that we can get that last block going. Okay, so that's really the idea. So that in essence, once we finish, we will end up with a model, right, So we will end up with a model that will sort of look like this. So we have, let's say, the original message, M, of size 128 bits. 128 bits, right? And we're going to have over here the original key. And then that key is going to be K1. But so that now it becomes the round keys. So you'll see what the round keys are going to do. Basically, we create all of these from the original key. Then here I can say dot, dot, dot. And then over here, I have KN. So you can define how many keys you have. You know, it's just a parameter in the algorithm. And then once you have this, what do? You take the original message, right? You take the original message, and now you're going to apply the round function where you have your input is K1, right? And then your other input is going to be M. Do you see that? And then the output, maybe I should make that. And then the output of this is going to be now, let's call it M1, just to keep it simple. And then now M1 will go into the next round, which will use K2 and M1, right? And then that gives you M2. And then once again, you know, you perform another round, K3, comma M2, and so on, right? So this, you know, the output of this is going to be M3, and then this will continue, so dot, 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 until you get to the last round. And in the last round, you're going to do R, K, N, and then let's just call this one here. These are usually 2, 1, 3, 1. So this would be MN minus 1, just to be consistent there. And then now you have, and the key goes in. And then the final output of that is going to be quite simply your Cipher block. So I should say this is a block. And this one's also a block. And what would be the size of this one? How many bits? You should know that from the definition, right? So what's the size? It's one thing I said today. No one? So it should be 128 bits. Remember, it maps, the definition is maps n bits to n bits. So then this should be 128 bits, okay? So that's, you know, that's basically your algorithm right there as far as, you know, as far as this is concerned. So that, you know, that's the approach, the general approach of block ciphers.
So with block ciphers, is it the very last block where padding and stuff would be added then, right?
That's right. This is
Okay.
what I just described here is just one block.
Right, okay.
All blocks, so all blocks will always be 128 bits. When you take the original message and you create the list of blocks, if that last block is less than 128 bits, it gets padded, but it gets padded before it gets here.
Okay, so before it actually gets to this. Okay,
Yes.
all right. Yeah, that makes sense.
All right. Any other questions? All right, so blocks of operation we've talked about a lot, right? So I'm just going to mention the terminology, modes of operation. We've talked about that. All right, so you know there's ECB, CBC, and so on. Right, so we're only, you know, they stand for things like electronic code book and things like that. They're basically different ways of encoding the blocks. It's like almost like saying you're just going to change the order in which you do things. In some of them, you have a initialization vector and so on. Okay, so that's really the idea, and that's one of the things that we will get to today, hopefully. Or maybe not today, but just be aware that that's part of it. All right. Okay, so now we are going to look at the procedure for just one of these modes of operation. Given that we already know the definition, yeah, so we need to take a message, break it up into blocks, pad them if necessary, and then decide on the chaining mode. So mode of operation is also sometimes called a chaining mode. Or let me just say this more formally. Block ciphers use a chaining mode. So use a chaining mode. Okay, and so that's what we have to understand a little bit more. And it just indicates how to encrypt the blocks. So how do you go from M blocks to C blocks? All right, so this example actually is best understood with a diagram. So I think it'll fit here. This is going to be CBC, which also stands for the cipher. Stands for cipher block chaining. Okay, so the cipher block chaining. All right, so how does the algorithm actually work? What chapter? Okay, so I'm getting a question. What chapter in the book goes along with this? I don't have the book in front of me right now. Give me a sec. So this is symmetric key. Actually, I remember seeing this in chapter, I think it's the first chapter. So in the secret key chapter, which is chapter 21, so where it starts talking about DES and AES, encryption modes. Well, pretty much what I'm going to talk about right now is figure 21.5. So page 479, section 21.4.3, cipher block chaining CBC mode. So does that answer your question? Yeah, so that's, 21, yeah. So that's kind of what we're doing right now. As I said, I'm getting into some of the details of the algorithm itself. All right. Okay, so let me put the book away. Okay, so the idea is that you know, as I was saying, cipher block chaining, you know, we gotta remember what I want you guys to do is ultimately to understand the Python code that I'm gonna give you. But we're gonna do this, we're gonna implement this algorithm for sure in that. So the idea is, first of all, we have some plain text messages. We have plain text messages here, right? We have plain, let's say plain 1, plain 2, plain 3. All right, and then this is where it gets tricky because we know we want to arrive at ciphers, right, which are going to be of the same size. We know that for sure as well. So the question is, how are we going, what's the order in which we're going to perform all these steps ultimately? All right, and that's where ECB and CBC are different. It's in the order that they follow. Okay, you can see, you know, since you guys have the book in front of you, you can see there that you're going to have two diagrams, a diagram for ECB and a diagram for CBC. I'm only going to do the one for CBC, but you guys can explore the one for ECB and notice where the difference are that, you know, make the algorithm less secure. All right, so the first, you know, we know, of course, that we're going to use an XOR operation, which we will have defined in Python. Then we will have an initialization vector. Okay, this is going to be called the IV. And that's just because we need something at the very beginning to XOR. Okay, once we have that, we have some kind of an algorithm, the block cipher encryption, let's call it. Right, additional steps, and then given that we're going to have a key, right, and that will produce C1, the ciphertext. So this is just our encryption. Then after that, plain text 2 comes in. It's going to get XORed. Oops. XORed. All right, this XOR operation will need to have an initialization vector. In this case, it's gonna just be the previous cipher 1. Previous cipher 1. Here we need to bring in the key as well, and the key used with the encryption function will give us the new cipher, cipher 2. Okay. Then we just keep going with this process. So this is something that we're going to have to implement, and we will implement this via for loops. Okay, so now P3 comes in. It's going to get XORed. It's going to get XORed. This then goes like that. Right, it's gonna, you know, it becomes the input. We have a key, maybe the round keys, maybe just regular key. Goes into my encryption function. Because there might be, you know, what's going on in those functions is that there might be additional steps. But ultimately, the operation is an XOR operation. And then from there, you get C3, and this would be the CBC method, which is, you know, more secure. And that's it. That's sort of the algorithm that we have to implement. Are there any questions about this?
I don't think so.
All right. Good. Pretty clear. Pretty easy. Okay. So now that we've talked a little bit about that, we are ready then. We've talked, so as you saw, we talked of a general symmetric encryption algorithm, and then we talked about modes of operation, chains, mode of operation. And now, before we're ready to write the code, all we need to do is look at AES. All right, so, or sorry, not AES. We're gonna do the data encryption standard, DES. At least I'll get started with it. I might just cover it a little bit and then cover it again next time around. Right, so let's go ahead then. Now we are ready to look at one of our block cipher encryption algorithms called DES. Okay. So DES, as we saw in the slides, is the data encryption standard. And although, you know, it's not considered secure anymore, it's still the most studied algorithm in cryptography, right? You know, that was the most studied. And as I said, AES does not depart from this. It's not like RSA, I would say, okay, departs from this. So we need to study both of those algorithms. But AES departs a lot less from DES. And so therefore, I think for our purposes, for this course, understanding DES is good enough. And we don't need to look into AES. That's my opinion. All right, so so again, the reminder of block ciphers, quite simply, is that you go from n bits to n bits, right? So that's, you know, really the ultimate goal. So I'll rewrite that. So the plain block, the plain text, let's say plain text block. All right, it's going to be, you know, we go from n bits. We're going to, you know, we have an encryption and decryption going there because it works in both directions. And then we have, of course, the key, k bits, and that's going to give you the cipher block, which will be also n bits. Okay, so that's basically the algorithm that we're trying to do. So just a little bit of, I always like to put things into context and history. You know, I like that. So the data encryption standard, basically, created in the 1970s, right, at IBM. So before, you know, Bell Labs and, well, I wouldn't say before, but another group that dominated during that time that you could expect things from, besides Bell Labs, yeah, that's a better way of putting it. So another place that you could expect results from in that era, other than Bell Labs, would be IBM, MIT, places like that. All right, so in 1997, think about it, DES was broken. It was broken, and by exhaustive search. So basically, you know, by a lot of keys running, you know, like a dictionary type of an attack. Around 2000, so in 2000, let's say, AES was adopted, right, which is a more advanced version. Okay. So now, but let's just look at DES and let's just see how it works. Right. So the basic, so DES is really the way that I would say, if somebody asked me to describe DES, what I would probably say is that it's a block encryption algorithm, breaks the data into blocks, and then it's got these little mapping functions. And what it tries to do with these functions is like it's jumbling the blocks. So you know, a block is broken into two parts called left and right, and then the left right becomes the right part, and the right part becomes the left part, and they get shifted, and then, you know, it's little tricks like that. That's how I would describe DES. However, it's got a more formal definition, and that is that it uses what is called a Feistel network. Okay, so it uses a Feistel network, and so that's what we're going to see right now. All right, so the basic idea then is that it uses what is called a Feistel network. So let's write that down. So the basic idea is to build what is called a Feistel network. Okay, so that's that's really the idea, and these are basically mapping functions. So given functions f1 ... all the way to f, let's say d, right, the size of the network, these functions map n bits, again, to n bits. Okay, so they map n bits to n bits to n bits, and then finally we can say in some scheme. And really that, that's just going to depend on how you implement your algorithm. Okay. And this can be formally defined. So formally we can define this f1 ... all the way to fd as a mapping of 0 to 1 sequence of n bits, right, that gets mapped into another 0 or 1 sequence of bits of the same size n. Notice that both of these. So that's a very important parameter, right, because it determines how the function will work. All right, so now comes then, what is that so-called scheme, right? So, so let's define the Feistel network. Let's go ahead. I'm going to define the Feistel network here. So I'm just going to say the Feistel network. All right, an example of it. So I have a block, right? And the block is, I have a block. And to make this easier to understand, we're going to say that the block is of size 2 n bits, right? So 2 times n bits. All right, so given that, then now we have a block over here. It's probably too small. We have a block over here, all right? And this is going to be our input. Okay, so that's our input over here. And then it's 2 n bits because we're going to think of it now as being divided in half. Okay, and so each one of these will now be n bits, and this one will be n bits. All right, and then now we're going to call these right and left. Right, and we're just going to keep track of where we are. So we're going to say that that is 0. Okay, pretty simple there. Now here is where the whole jumbling comes in, and it does get a little bit more complex, but fun. If you like puzzles, it's a lot of fun. And so now this is going to change a little bit because this is going to be now L1 or left 1, right? So I'm just shortening it. And this one is right 1, given that this one is right 0. But now things have to flow in a certain way. So the right block 0, is going to basically do that. So it just literally, the right block 0 will become left block 1. Nothing else changes. However, To calculate R1, we have to do a little bit of more work. So what's going to happen is write block 0 will also flow in that direction, the same block. But it's going to go through a function called F1. What is that F1? That's those mapping functions that I was talking about, right? Which are simply defined as going from this, mapping from that to that in some scheme. Oops. And so now, that's a function. So that function will take the block and change it, but it's still going to be of the same size. And what comes out of this function is the modified block, which is now going to take the left 0 block, and you're going to perform an XOR operation. So there's the XOR again. And then once that has been done, that will become write 1 block. So write 1 block is actually a modified version of the previous 2 blocks. Okay? Now the Feistel network will continue in the next iteration of the network. We're going to have now R2, and we're going to have L2. Okay, so we're going to have both of these. And now, same thing. R1 goes like that, R1 to L2. And then, so by that logic, what would happen here? R1 needs to go through F2, right? F2. And the output of that, the modified version of that, takes in L1 XOR, right? XOR. And that creates R2. You see that? This is the whole, jumbling of things. Then, it keeps going, ... until we arrive at somewhere around here. We're going to call this one RD-1 and LD-1. Okay. And then now we are going to do the last step. So we need to define RD, LD. Notice that this is going to be our output block. It's still this is 2n bits, and this one will still be 2n bits. Okay, so the blocks are still the same size. We've just jumbled everything up through some scheme. So then here once again, RD-1 just slides down, becomes LD. But RD-1 must also go through FD, right? FD over there. And then that gets XORed with LD-1. You XOR those. And then now this slides and becomes RD. And that's it. That's the Feistel network. Is this clear? Are there any questions?
I think it's pretty clear.
Excellent. Excellent. All right. So, therefore, in conclusion, we can say, given this, so I'm sure you guys made a note of this, we can conclude that let's see, therefore, Li will be equal to Ri-1, right? Do you all agree with that? So for instance, Li is Ri-1. L1 is R0, right? 1 minus 0. Right? Pretty straightforward. Then for Ri, we're going to say that we are going to take Ri-1 through the Fi function, and then we're going to XOR it with Li-1. Oops. like that, right? So we're going to say that Ri, if you're looking at your graph, Ri, let's say Rd is, we take Rd minus 1 through the Fd function, right? And then we XOR that with Ld minus 1, right? If you're looking at your graph. So this is useful because this is when you were writing the algorithm, the script, you know, we're going to have to write the formulas like that, assuming we had all these. And of course, f still needs to be defined, but we're just treating it as a function at this time. You'll see later on, I'll define what the function actually is. Is that clear for everyone, guys?
Mm-hmm.
Okay, great. Some questions? Yes, all right, great. So what direction was I going in? I was going in that direction, correct?
Yes.
And what would that mean? What am I doing? What am I probably doing? I'm encrypting, right?
Oh, yeah, that's what you meant by that. Yeah.
Most likely. Okay, yeah, that's what I meant. So now, what about reverse? Because if I encrypt something, it's not useful, right? Unless I can decrypt it. Would you agree?
Correct.
All right, so here is where this is going to get interesting. You guys, I'm going to give you although there's no homework, I'm going to give you a short quiz. Okay, it's a fun quiz. You can submit it. I'm going to give you, I mean, I'm sure you can solve it in minutes. So, but I'm going to give you it's 5 o'clock right now. So I'm going to open up a Dropbox on Brightspace, and I'm going to leave you guys until, let's say 10 o'clock tonight, right? And it's just one short little problem. Write it up in your Word document, and you just have to give me the following, okay? So we're going to call this a little pop quiz. And then after that, I'm just going to open it up to questions, or you can work on this. All right, so I'm going to, pop quiz until, okay, I'm getting some requests to keep it open until midnight. That's fine, I will do that. Yeah, midnight is fine. So it'll have to be tomorrow at 1 a.m. Eastern time, which is noon, something like that. It'll be something. I'll probably just leave it open until 2 a.m. tomorrow so we don't have the issue of the day change. All right, so until 2 a.m. Friday, I guess, Friday morning. All right, but it'll be actually, this is Eastern, so keep that in mind. All right, anyway, the quiz. You call it the decryption part, or the reverse, if you'd like, flow in that direction. So so let me just write it out here in words and let you guys figure it out. Given the previous logic, how would you invert the process? Okay, so what I mean is you have to look at this, right? And now you just have to give me the inverse flow. What I'm looking for is these, okay? That's your answer to your quiz. You just have to give me these two little formulas. But you have to give them based on the problem that I'm going to write here. So I'm saying, given the previous logic, how would you invert the process given me over here, let me just be a little bit more. So I'm going to say based on the previous logic, how would you invert the process given the following? All right, so you have to, so I'm going to give you this. So you have to write your answer in terms of these parameters. It's still the same logic. I'm not changing it. I'm just changing the indices of all the variables, okay? Okay, and then still the same logic. Okay, so what I'm looking for is, remember, you're going now in that direction. Therefore, I need these values, okay? I need those values given these values, okay? So don't give me the answer now. You need to, this is a pop quiz, so if you want to get credit for this, you need to submit the report. It's individual work. So the question is, what is RI, right? So I need that. So RI written in terms of these and this logic, but all the previous because you're going in that direction. And also I need the answer, what is LI? So this one. So these two, RI and LI, I need you to write them down. And that's it. So it's short. I mean, you can do it in a few minutes or take however long you want, but that should be it. And that's it for today then. Work on this. Are there any questions? Okay,
When
so
will you be posting the lecture for today?
I'm sorry, say that again.
When will you be posting the lecture from today if I need to refer back to what you said?
Good point. I didn't think of that. The video, so it'll take me about an hour for the video to upload. I'm gonna start generating it in a second. And so maybe it'll load on the YouTube channel, right? So you guys can get to the YouTube channel just by going to the website. And then in there, I have a link called YouTube channel. You can go there. Before I can actually link it to the website, I have another class today. And so it'll take me a little while. But, oh, you want to screenshot it? Sure, I can. So screenshot this one and screenshot that one and this one, right? That's what you want. Yeah, so it'll take the video, it'll take a couple of hours for it to load. But it should definitely be there, I think, by 8 o'clock. It should be on the YouTube channel.
Thank you.
Any other, but you'll have until 2 a.m. to work on it, so that should give you enough time, I think. I mean, it's not, don't overthink it, right? It's not, the answer that you're going to give me will look, that's it. I mean, that's it, except that when I gave you this, of course, it was in one direction. Now it's in the reverse direction, and I've changed the term. So I want you to write things in that way, okay? Are there any other questions?
I don't think so, not right now at least.
Okay. This will be worth the same as the lab, so take it seriously, and do it. It's easy points. I think it's it should be a lot of fun. So I'm gonna go ahead and create the Dropbox for this, so I don't forget. So I'm gonna go over to I'm going to go over to Brightspace, and I'm going to create a new module, and I'm going to call this Feistel Network quiz, okay? All right, so that, should be it. I'm going to move this up to about here. And you all understand, so I'm just going to say complete the quiz as discussed in class. Okay. And then this is the Feistel Network. Quiz. And it'll be due tomorrow, I guess. But at 2 a.m., which is 1 a.m. So 2 a.m. should be 1 a.m. Central. Complete the quiz as discussed in class. And it'll close at that time, guys. I'm not gonna leave it open after, so just be aware of that, okay?
Okay.
Okay, great. And that's it. So start working on it. If you want to take screenshots of something right now with your phones or something, or your laptops, just let me know what slide you want me to go to, and I can do that. Otherwise, just start working on it. If you have any questions about anything else, I'll be here. All right?
All right, cool. Thank you.
Okay, great. So I'll be here. If you start working on it, you have, like 30 minutes right now. Work on it. And if you need anything, let me know. And just the Dropbox has been created. The link is there. You should have some kind of a link there for you to attach files. Submit a Word document or PDF. And that's it. All right, so I'll be here. I'm going to mute my microphone, but if you have any questions, let me know.